McCann. I am a software developer at Jobber. Been working on web development for a few years, and this is my presentation on the JavaScript event loop. So one thing to note is that JavaScript is single-threaded, which is often something that people confuse asynchronicity with being a multi-threaded application. That means that we only ever do one thing at a time. So that means if you have two pieces of code that are running, you can guarantee the method that you are currently in will finish executing before anything else runs. The only exception to this is web workers, which will spawn up a new thread. That new thread will have its own event loop. So why is JavaScript asynchronous? The only real reason is that blocking I/O degrades the user experience. So if you clicked a button and then the entire screen froze while code was executing, you would probably be really annoyed, especially on like any modern application. So in order to solve that problem, JavaScript has the event loop. And in essence, the event loop is fairly simple. It's probably more complicated in actual implementation, but the gist of it is we just wait for a message to go into the queue. When the message is in the queue, we process the message and then continue waiting again for the next one. So I'm going to quickly walk you through. So processing a message will be represented by this arrow moving from the event queue into the call stack. The waiting for a message will take from the browser land into the event queue, and then our code will be on the right side. So this entire presentation will be almost just walking through code and visualizing how it goes through the event loop and into the console. A few rules about the event loop. The first is that events in the event queue will never be fetched until the stack is empty. So if there is anything on the stack at any given time, the queued events will not execute. And the event queue is a first in, first out queue. So on the right, I have my example code. In a moment, you'll see a little red pointer. That is the current line of code that is being executed. In this case, we're grabbing the button. That goes onto the call stack, moves into the browser. So we actually fetch the browser or the button from the browser APIs, and then we move on to the next line. In this case, we grab the button, add an event listener to it. The browser saves that in memory somewhere, just knowing that at some point a button's going to be clicked and it has to create an event for it. And now we're going to move into the foo function. So as you can see, foo moved onto the stack. And as we start executing code within foo, it will just get put onto the stack on top of foo. And that's the way it'll go for all of these next few lines of code. So we log to the console. Message goes into the console. We set a timeout. So again, we're saving that timeout into the browser. It does internal stuff and sets a timer to execute the OnTimeout function at a given point in time. We're going to add a second one. Okay. And now we're entering the bar method. So as we try to log console.bar to the console, the first timeout we set got reached. So rather than stopping execution and immediately running what was in the timeout, the browser just pushes the OnTimeout function into the event queue and continues running the code that it was currently running. So it will log bar to the console. Bar then comes off the stack as we reach the end of the bar method. Now we're at the end of the foo method. It is not yet off the stack, but a button was clicked on the page. So again, the browser doesn't interrupt the current execution. It just pushes something else, the click event handler, onto the event queue and moves on with executing the code that was currently running. So now that foo has actually left the stack and the stack is completely empty, the browser knows that it can pull something from the event queue, and it will pull the first thing that was pushed into there, which is the timeout. So now OnTimeout is on the stack. We enter the OnTimeout method, and right before we do the console.log, the other timeout is pushed onto the stack. So I'm going to quickly walk through this. Timeout is now logged. We exit the method, and again, stack is empty. Next thing goes in. And this will continue until we are done the program. And now that OnTimeout is left, we've finished executing all of our code. The browser is just sitting there waiting for click events. But that's the end of this little example piece of code. And I want to give you a few notes about some things that you can guarantee within the event loop. One of them is that setTimeout for any given time does not guarantee that function will run in, say, 1 second or 1,000 milliseconds. It only guarantees that it will run after that amount of time. So if you had a setTimeout that was in the event queue and you're currently executing code was continued to run for 30 seconds, that would delay the amount of time before the OnTimeout rendered, making it maybe 31 seconds, which you were not expecting. So never guarantee or work under the assumption that the time you give is the time in which it will execute. Another one is that if you call setTimeout with 2 arguments, A and B, within the same context and in that order, if A is less than or equal to B, you can guarantee the execution order will execute A first and then B. So if you have 2 setTimeouts in the same function, and they both, say in this case, instead of 1,000 and 3,000, they were both 0, you could guarantee that the first one would execute before the second. Right, and I have a little link here, which if you get the slides later, will take you to the spec doc. The number, the C number 16, changes week to week. Basically, whenever they update the spec, that number just gets pushed up or down, so that is not super valuable. Other point I want to make is that renders may trigger in between items in the event queue. So as things are coming off of this event queue, instead of grabbing from the event queue, the browser may actually just re-render the page at any given time. So I don't think many people actually think about rendering too much, so you will never really rely on that fact, but something good to know. Only exception there for when it'll render is if you force a render by grabbing something from the DOM and like checking its size or one of the DOM events that forces renders. Otherwise, it will try and render between events in the event queue wherever possible. And that's the basics of the event queue, which seems pretty easy, kind of. So I'm going to quickly walk through another example. I've gotten rid of the browser land so we can get through it a lot quicker, just so we can quickly see what we would expect to happen in this given situation. And I say expect, and don't read into that yet. So what just happened is we ran the foo method OnTimeout and OnPromise1 both got pushed into the event queue. When OnPromise1 finishes, it will push OnPromise2 into the event queue. So both of those finished. They rendered their or logged their output to the console, and now OnPromise2 is on the queue, and OnPromise2 is in the output. This is the expected output if you only know about the event queue. However, the actual output flips these. So OnPromise1 and OnPromise2 will happen before OnTimeout. This is not consistent across browsers, but most of them follow this behavior. Why? There's another queue that got introduced somewhat recently called the MicroTask Queue, which is for things that need to be processed in a more timely manner. One of those things is promises. Most browsers put them in the MicroTask Queue. Another one is DOM mutation event listeners are also put in the MicroTask Queue. But we can look at our old model and just adjust it slightly and understand how the MicroTask Queue works. So as you can see, the MicroTask Queue I've positioned above the event queue just to indicate that it has a higher precedence when it's fetching events. So it works similar to the way the stack does. It cannot process events unless nothing is on the stack. However, the event queue will not process if there is anything in the MicroTask queue to process. So you could actually potentially block the event queue from ever executing by constantly pushing things onto the MicroTask queue. But that would be really dumb to do. So if we go back to our old example, both OnPromise1 and OnTimeout fired. OnTimeout fired first, so it got pushed into the event queue first. Then OnPromise1 was pushed into the MicroTask queue. At this point, when foo comes off the stack, onPromise1 is fetched first because it's in the MicroTask queue and it is a higher precedence. So it will execute its code and push onPromise2 also onto the MicroTask queue, which means, again, OnTimeout has to wait until onPromise2 finishes. And then OnTimeout1 can go into the stack. And now we get the expected output for what we actually see in most browsers. So back to the things to note. So I've left the first two the same, but I've added a little note about the MicroTask queue, which, as I said before, it executes as soon as it is able. One issue there is the browsers don't agree when as soon as it's able actually means. So one potential gotcha is so if you have a click event that triggers two different functions, some browsers will allow microtasks to run between those functions. Other ones will wait for both of those functions to finish before it runs the microtasks, because in their mind, one click event fired, even though it fired two different functions. So Chrome executes in between click functions. I think Safari executes slightly differently. So that's one little weird gotcha there. Another is what actually gets put into the MicroTask queue. I think all modern browsers now have promises in the MicroTask queue, but last year when I first wrote these slides, that was not the case, and most browsers didn't. Only Chrome and I think Firefox were pushing into the MicroTask queue for promises. I think they all agree that DOM mutation events should be in the MicroTask queue, though. And unlike the event queue, renders will not happen in between microtasks. The value of microtasks and the reason they were implemented was to reduce the overhead that happens in between every event in the event queue. So they wanted to reduce that as much as possible for things that could happen quickly. So yeah, rendering will not happen, as well as a few other things that I can't quite remember. And I'm going to quickly just go to a practical application, and this is actually why I ended up learning a bunch about the event queue in the first place. So basically all we're going to do is on the press of a button, so down here, we are going to add an element to the DOM. That element is a custom web component. Oh, yeah. There we go. So on button click, we're going to add something to the DOM. That thing is just this new element that I created that is called an XSpan. All that the XSpan does is has a method called foo on it that will alert to the window. So immediately after we append that to the DOM, we're going to log details about it and whether or not it is currently a web component. In a browser that natively supports web components, it will be. In a browser that uses a polyfill, it has some weird behavior. So at different points in the life cycle, we're going to log the details of the span to find out when it will actually become a web component. So in a browser that supports web components natively, like Chrome, when we click this button, immediately after being appended to the DOM, it is already a web component, and we can perform actions on it immediately. Yeah. So immediately after, it is a web component, and at all stages in the lifecycle, it's a web component. This is often the case that in our code, we were appending a web component to the DOM and then trying to perform some action on it. And in Chrome, that works fine. But if we look at Safari, what ends up happening is immediately after being appended to the DOM, it's not yet a web component. The reason for this is we were using a polyfill, which has a DOM mutation event listener that initializes the component as a web component, and that mutation observer is actually pushing things into the MicroTask queue, so it's still waiting initialization. So we had a few bugs where this would happen, and then we would try to initialize the component with some data, and it wouldn't work. The only way that we could actually do that is by adding a setTimeout, or we could have used a promise resolve to actually wait until the MicroTask Queue had a chance to flush before we actually did any work on that web component. And that is, my entire presentation. So there's a few resources I used to generate this list, or to generate this presentation. These are all really good talks and explanations about the event loop, MicroTask queues, and everything else. One of the very cool things that were built is this tool made by Philip Roberts, who does a really good talk on this, but you can visualize how the event queue actually operates on any arbitrary code that you can write. So it's a cool tool. You can just like see how everything moves around. Yeah, super useful. You click a button click gets added. Yeah, that's it. Any questions?
Yeah, what are the differences between a browser event queue loopy thing versus Node.js event loop, if any?
I think Node.js uses the Chrome engine, so it will behave similar to Chrome.
Does it have a micro queue task?
Yes.
Node.js?
Yeah.
Oh, interesting.
Yeah. Or at least I'm fairly certain.
So it seems like this setTimeout0 thing is this pretty useful tool where when you call setTimeout0, basically you're stating run this code after everything currently in the MicroTask or event queue has run, which seems like a pretty useful tool. But setTimeout0 is like really hacky. Like, did you get much of a sense of like how accepted of a workaround that is? If there's any talk about like some, like even just some syntactic sugar, so you're not doing like a setTimeout0 to accomplish something similar?
I think the vast majority of the time, setTimeout0 is probably not the right approach. It would be to create an event and then fire that event on the object that you're listening for, or even this occasional good usage of it is like polling a server and waiting for a response. And again, if you have more modern stuff like WebSockets, you can again wait for an event, so you're not actually doing these like regular checks. One case where I've seen it used well, I think it's Ember's Backburner and a bunch of those other like scheduling apps. They use promises and timeouts in order to like actually schedule events, in order to like create their own internal event loop that lets them render things easier.
I was going to say there was actually kind of an API that was out there for a little while called setImmediate that did sort of like that. We would just like set timeout with a 0. But I don't know what happened to it. I know it says Gecko and WebKit were kind of against it. I don't know what the reason for that was, but yeah.
There's also a new API called, I think it's setIdle_callback. And so that's for setting any code which doesn't have to run immediately and should be delayed till after anything. And it not only waits for the event loop, it'll also stagger between rendering and animation so that it doesn't cause animation to lag.
Nice. Cool.
Exchange.js is Edmonton's JavaScript meetup. Thanks to our sponsors, Jobber and Investopedia. Support the meetup and like and share this video, and stay informed by following us on Twitter and meetup.com. Links in the description. See you soon!